Welcome to this presentation on generalized minimum variance control, abbreviated as GMVC. I will explain the need for it, we will derive it, present an example with Scilab code. We will also discuss the approximation we will make and the utility in using GMVC. Minimum variance control results in large control effort. The question is, can we constrain the control effort and use it? Can we derive a control law with this constraint? We arrive at the method of generalized minimum variance control. We arrive at the generalized minimum variance control. Here is the model of our system, R max, and where we have divided C by A into E and F and then arrived at this expression. Here is the future noise term. What we will do is, we will now minimize variations in Y at K itself, but with the additional requirement that we will constrain U. We will not allow U to become very large. So here is the objective function that we will minimize. We will minimize multiple of U squared using a tuning factor called rho. If the control effort U becomes very large, we will increase rho, the weightage, so that when we minimize this objective function, U will automatically get reduced. We will learn more about it later on also. For now, we will include rho as a tuning parameter that is used to reduce the effect of U. We will also include this additional term gamma times R. Recall that R is the reference variable or set point, and then we will see the value of gamma subsequently. It is very similar to the gamma that we used earlier on when we were discussing pole placement. So we need to minimize this objective function. So let us substitute for Y from here. So we get this EKB plus FKY is coming here divided by C, and then plus EK of Cn plus K, that is for the first term. Then we have gamma into R and this whole squared plus rho times U squared. Now we have to evaluate this. Notice that when we take a square of this, the cross term need not be considered. That is because C of n plus k is the future noise. It is not correlated with the current input, current output and so on. When we remove that cross term, we get the following expression. You have the square terms, one for this term without this cross term, and the square term of C is written separately, and then we also have the rho U squared coming here, and we need to take the expectation of this and also the expectation of the future noise term. We can see that the second term, that is the noise term, is 0 because the expectation of future noise is 0. So we can 0 it and we have to minimize the first term. So we need to minimize this term. We differentiate this with respect to un. We need to minimize this by suitably choosing u. So we differentiate with respect to u and equate it to 0. We get twice of this term times derivative of this term involving un. So we write it as alpha 0, and for this 2 times rho u of n equals 0, and alpha naught is the constant term of EKB by C. So when I substitute, I get this expression. Now let us collect all the terms to one side. On the left hand side I have all the u terms I have a u term here, I have a u term here, so it comes here, and then the y term fky comes here with a minus sign, and then gamma cr, it comes from here. I have written it in blue because I would want you to write this down. We are going to require this 2 slides from now. In particular, I am going to ask you to remember this alpha naught EKB plus rho c, because this will come in the denominator when I calculate the expression for u. So you may just want to write this down. We need this 2 slides from now. Alright, here is the example. This is the same example that we considered earlier for the when we discussed minimum variance control, and we obtained all of this E1, F1 and so on, but now we will use this to arrive at GMVC with rho equals 1. So remember that alpha naught EKB plus rho c that we had it in blue 2 slides ago. Here is the control law, and recall that alpha naught is the constant value of EKB by c, and EK was 1, E1 was 1, this is B and this is C. The constant term of this is equal to 0.5. When I substitute these expressions into the first equation, I get this expression, and when I simplify, I get this. I would like you to simplify this and make sure that you get this. Now the question is about alpha. How do you find alpha? We have still not explained how to find alpha, other than to say that it is similar to the term that we used in pole placement. I will also give a hint. At steady state, y should be equal to r. Based on that, you can determine gamma. The second term is to be calculated. In fact, in the next few slides, I am going to show Scilab code that calculates the second term. So we have GMV underscore mac1.sce. It's also given to you. When I execute this using the function called GMV, it's here GMV.sci. I also make use of the function CL.sci, and after invoking I call SC and RC. You get these values. These are exactly the values that we obtained in the numerical example earlier. I would like to make a caution that GMVC is only approximate. Recall the differentiation of the optimization index. We differentiated this with respect to u. We just went inside and differentiated as if we could do that, but it is only approximate. In reality, you cannot do that. You need more rigorous methods. This is studied in detail by McGregor. The correct method is to use linear quadratic Gaussian method. The details are in the textbook. Both theory and examples are presented in the textbook. Nevertheless, GMVC is popular. Although only approximate, GMVC is quite popular, especially amongst Japanese researchers and practitioners. The reason is because of ease of derivation and adequacy. This is used extensively in adaptive controllers. The textbook explains how to tune a PID controller using GMVC. This method is derived by Yamamoto, Inu and Shaw. Remember, PID tuning is a difficult problem, and to arrive at the first set of parameters can take a lot of time. As a result, this tuning method by GMVC is extremely useful to the researchers. This is another reason for the popularity of GMVC. What next? both minimum variance and GMVC minimized variance of y at the immediate possible time instant k, where k is the delay, results in large control effort. This is one of the disadvantages of both minimum variance and GMVC. GMVC itself is an improvement over minimum variance for the same reason, but sometimes GMVC also is not good enough, and this problem is overcome in generalized predictive control, also known as GPC. In GPC, the minimization is done over a time interval. GPC is one of the model predictive controllers, and it will be studied subsequently. We will devote a whole week to study GPC. With this, I have come to the end of this presentation. Thanks for joining. Goodbye.